Next speaker, Alessandro Magnosi, is a cybersecurity consultant with many years of experience. He's part of the security testing team at BSI, which is the UK national standards body. On top of his normal work, he works as an independent researcher and OS developer for Porchetta Industries. His talk is The Bright Side of the Moon, exploring novel techniques for bypassing cold stack analysis. And so, I think they're changing the computer. Everything fine? Almost? A few. Windows updating, okay. All right. Ready? Okay, thank you. Alessandro Magnosi again. Thank you.
Perfect. Okay. Doesn't present? All right. Great. Thanks a lot for attending. So in my talk, The Bright Side of the Moon, we will explore novel techniques for bypassing cold stack analysis. I mean, I've been already presented, so I think we can skip this. Just if you want to get in touch after the talk, I go as klezVirus on Twitter and GitHub, and I'm on all social networks as Alessandro Magnosi. So you can, if you want to hit me up, please do it. So for today, I'm gonna just introduce the concept of stack spoofing, and I will give you some definition about the topic and some related Windows internals. After that, we will explore already presented techniques for stack spoofing in practice, and then we will explore our novel technique that we called Stack Moonwalking. Of course, this is the theme for this event is attack and defense. So we will also provide you with some engineering detection, some detection engineering around this technique, and then I will leave you with some unanswered questions and where you can find them, and also future research avenues. So let's start. Why thread cold stack spoofing? Of course, on Windows, when you start a program, you automatically create a process which acts as a container, and then one or more threads are actually tasked with executing your main code, the main code of your executable. Now, every thread maintains a stack, which is memory location, which maintains the information about all active subroutines in a given thread in a given time. Now you can imagine the cold stack as this. And every frame in this cold stack is describing a function and contains the local variables, the context, and other space, and the space that is needed for the function to execute correctly. Now, for spoofing instead, what we mean is that we will tamper with this cold stack, and we will replace the frames in a malicious way, usually to bypass some sort of detection. There is no legitimate use case for stack spoofing whatsoever. So these are 4 examples of cold stacks, and as you can see, there are some similarities. In Windows, you may have like 2 main categories of threads that are loading something, and they will start with LDRP load DLL, or you can have executing threads, and executing threads usually have these 2 frames in common, which are the thread. I will refer to these 2 frames as thread initialization frames. And those are the RTL user threads start and base thread init. After that, you can see that there are some frames associated with the program you're actually running. And above those, there are the frames that are actually executing Windows APIs, which are APIs exposed by the Windows operating system itself. Now, the cold stack, of course, is dynamic in nature. So how do you calculate it? So in Windows, I mean, if you remember how it was working, if you are aware about the Intel 86 architecture, you know that in 32-bit you had a specific prologue for functions that was literally just pushing the base pointer and then moving the stack pointer to the base point and allocating an additional stack frame. Now, this, in a nutshell, how this was working is that every time in the context of a thread, there was the EBP pointer and the ESP pointer, and they were referring to the base of the frame and the end of the frame. And so you could literally, at any point in time, you could literally just refer to the start of the frame, move the ESP back to the start of the frame, then pop back the EBP, and do it again and again till the bottom of the stack. And this is like what we say, following the EBP chain till the bottom of the stack. In 64-bit, specifically Windows 64-bit architecture, we have RBP and RSP now, but RBP is a general purpose register. We don't have it anymore referring to the base as a base. It's no longer a base pointer, and it doesn't refer to the base of a stack frame. So RSP is the main register used both as a base pointer and a stack pointer. Now you may wonder, how do I maintain the location of the previous base pointer or the previous frame? So this is achieved instead of using the start and the end of the frame. We will use the RSP to refer to the end of the frame, and then we will dynamically calculate the sides of a stack frame. So in order to do this, of course, RSP needs to stay static for all function execution. Indeed, in Windows 64, RSP needs to be static for all a function execution, throughout all a function execution. The only place in a function that RSP can be changed is the prologue, and this is actually used for calculating the stack size. How? So when you compile a binary on Windows 64-bit, all the information about what is done within all prologue of any function is stored in the pdata section of the binary. In the pdata section, there is this exception directory, which is a table with all these runtime function objects. And these runtime function objects contains the information that is mainly useful for exception handling. I'm not going into the exception handler of Windows because it's overkill, but what we need to know for calculating the stack is that the runtime function contains the an unwind infrastructure, the unwind data, that contains an unwind code array, and in this unwind code array there is registered all the operations that are performed within a prologue. Now, probably you understand where this is going. So while if I loop through all these operations, I can find dynamically all the operations that are performing, that are modifying RSP in a certain way, and there are like these operations like push non-volatile register or alloc small or alloc large are mainly used for modifying RSP, and by just calculating the stack size, of course, a push non-vol will modify RSP by 8, an alloc small of a small portion, an alloc large based on, of course, of a larger allocation. And calculating all this modification, I can dynamically find the stack frame size. Now, once I have RSP and the stack frame size, I can just roll back and understand where the return pointer is and everything else, and do it for all function in the cold stack. Now, why do we care? We do care because when we execute malware on Windows, we can create anomalies that can lead to a detection. So in particular, we are concerned with in-memory execution, so reflective loading, and indirect system call invocation. So in memory execution, so reflective loading, what we have usually, if we consider the basic case, when we allocate something on the heap, we mark it as, we write on it and then we mark it as executable, and we execute from the heap, we will actually end up with a non-resolvable stack frame. Now, you may easily understand why it's not resolvable. As I said, to calculate the every stack frame, you need to use the information contained in the pdata section of a binary. Because this code was allocated dynamically, there is no pdata section, there is no exception information, it's not possible to resolve it. And this is, of course, an anomaly. If you call RTL virtual unwind on this, it will not unwind back to the bottom, and it will be a source of detection. If you think that using module stomping or function stomping will actually help, well, you're half mistaken, just because if you overwrite even a DLL, so you have a file, you are backed by a file in memory, you will still produce a call stack which is abruptly, like is missing the thread initialization frames. This, of course, also can lead to a detection. Like if I can even automate this. If I call a function and the stack is not unwinding, I can dump the last symbol, I can check the DLL, and then I can do a match between the text section on disk and the text section in memory, and I will understand that you performed module stomping. So it's not saving you. For indirect system call invocation instead, if you call a Windows, usually normal programs don't use NT API or indirect system call, of course. They use standard Windows APIs. And you can see that if you allocate memory using the kernel2 exported function, you have a stack which is step into kernel base, of course, which contains the real implementation of the function exported by kernel32. If you're using an NT API or you're jumping, you're doing something that is known also as tunneling back in the day. So you're trying to locate the interrupt, the syscall instruction in NTDLL, and you jump into it, you will produce this, which is easily detectable, of course, as well. Now, detection timings. When should I go and detect this stuff? Well, there are three main things, three main types of detection, three main timings when I can do this kind of detection. Periodic and conditional are pretty much the same. I scan the system every T seconds. I stop every thread in the system. I dump their context. I read their stack, and I see if there is something going on. The conditional is a bit less impactful on the system just because I just select threads that are already suspended or that are in a specific wait state. And usually delay execution and user requested wait state are the one we are actually interested in. But the best way probably is via hooking. So you can dump it through like placing a hook in a DLL or using kernel tracing, which is way better, usually in correspondence with, for example, an ETW event. You can dump the stack and check who performed the call and how. Is this implemented in real life? Well, probably the best implementation of this kind of detection is implemented by Elastic, which is doing great work. And they released a blog post like a few days ago, probably 2 days ago. And they released this blog post, and they implemented all this kind of call stack enriched analysis, where they check the call stack, and they can identify a lot of stuff. From suspicious process creation via reflection to suspicious remote registry modification. And this is all enriched and possible just for call stack analysis. Now, the technique that we presented, it was probably developed start of the year. And like just seeing, I mean, this is very practical consideration, but just seeing the implementation of this detection, we can be sure that this already bypasses these detections. Oops. So, and the reason is our technique is particularly indicated where the detection is mostly based on caller identification. For example, we can't do nothing about direct syscall via assembly bytes because, of course, you're just looking at the call site and you're exploring if there is a syscall instruction embedded in your payload. This is not possible. It doesn't matter how you call the syscall because you're embedding your syscall instruction in your executable. So we can do much about that. Or for example, evasion via LDRP kernel 32 is something we can do nothing about because it depends on the loaded DLL and not really on what we are doing from the main thread. So previously, stack spoofing was something created to protect a beacon or an implant or a malware while sleeping. A lot of the previous research is actually based on this. And stack truncation, return address spoofing, version 0.9, because it's a bit worse. Stack cloning and stack hiding are mainly this category of protection. Stack crafting is the only POC by William Burgess that try to bypass a specific kind of rule-based detection using Sysmon in order to open an handle to LSAS and dump it, if I recall correctly. So stack truncation is very easy as a technique. So what you do is, because you have something executing from the heap and you have this garbage in the stack, you try to solve the problem by locating a trampoline somewhere in a DLL or in your own executable, and you override the return address so that now you have a call stack that apparently has been called legitimately. Then you zero out whatever is after that so that the stack is cut, but at least doesn't show any anomaly. And what you end up with is something like this. So instead of having this, you have something like this. So this is a screen from Thread Stack Spoofer by Marius Manak. And this is the trampoline he chose to put in his own executable. I would recommend using a DLL instead of your own executable. But the technique is pretty much the same. If you want to know more, you can refer to Namazo POC return address spoofer on unknown cheats. Stack crafting is the POC from William Burgess that is trying to bypass Sysmon-based detection. And the idea is kind of simple. I want to execute something, so I will have something else calling the same function I want to call. So I stay on my system, I dump all the call to that specific function, I record the call stack, and then when I want to call the function, I just replicate the same exact call stack, crafting it artificially while I'm creating a new thread. This works, but it doesn't scale at all, because every time you want to execute something is not version compatible. You have problem of different builds in Windows. It just doesn't scale. You can have differences in stack frame size and stuff like that. Then there is stack cloning. Stack cloning was firstly implemented probably in Foliage by Austin Hudson, and stack cloning is a way to protect your beacon node from sleep as well. Is implemented in Ace Loader as well, and in Titan Loader, and probably something else. And the concept is kinda easy. Like, I know that I want to sleep with my beacon. I need to protect it while it's sleeping. So I know that it will end up, if I use a sleep, it will end up in delay execution. If I use a wait for single object, it will end up in a user requested wait state. I just search for a thread that is waiting in the same state I want to end up. So I search for this thread, and then I clone its stack. I go to sleep, then I need to use a technique which is in Foliage is APC queues. In another loader, I don't remember if Titan or in Nighthawk, is implemented using timers. But the concept is literally that. Stack hiding is sort of an evolution. Instead of using APC queues or threads, why not fibers, right? So the advantage of fibers in Windows, like, we don't really have fibers, we have thread fibers. They are called thread fibers for a reason. When a fiber is active, you can have just one active fiber in Windows per thread. And when the fiber is active, the thread practically have the same stack of the fiber. You can have more than one fiber as long as they are not active in a specific thread, and they all have a separate stack, separate variable, separate user workspace. Now, when I have my evil fiber in memory. When I want to sleep, I just create another fiber and switch execution to the other fiber. And my stack is clean now. And then when I want to go back, I just do the same, switch to fiber, and I'm again executing malicious code. And then and the process is repeated. Now, as you can see here, the stack, if you notice the address, the stack for the two fibers are completely different memory allocations. And now we have the malicious fiber, and there is also this stigma of the unresolvable frame, and while we have the sleep fiber, which is fine. Now, what is our approach? So our approach is a bit different from what we discussed so far, and it was designed to completely hide the caller from the call stack. It's been designed to obfuscate the call stack so that the frames that are chosen every time are different, so you can't really understand what is happening. And it's designed to auto-restore, meaning that you don't need an external mechanism to restore the stack after you finish execution. So you don't have timers, you don't have APC queues, you don't have external threads waiting, and you don't have fibers. So how this will work? Now, I just want to digress a bit, not really digress, just remember you that I told that RSP is illegal to change in the body of a function in Windows. So this is true, except that when it's not true. So when you have a dynamic allocation in the stack, allocate style, you are allowed to modify RSP, but you need to save it before. And so you literally restore the original function of the base pointer, and this happens when you find a setfpreg. So setfpreg is an operation that pushes RSP, saves RSP into RBP, making RBP again the base pointer of the current frame. Now, this is interesting because this is needed because when I'm doing a dynamic allocation in the stack, it's like I'm creating a new frame, an inner frame. Now, RSP is needed to be the new stack pointer, base pointer of the inner frame. So this is why I need to restore the original base pointer. But now we have a chance. When this is true, and I have this function, so this setfpreg is this, it's literally this function, just it gets propagated to the exception information. We don't care about this. So once this is true, now our RBP will contain the information related to the previous frame. So literally, the way the unwinder of Windows will understand where is the outer frame is thanks to RBP. So this gives us a chance. If we can push RBP on the stack and modify its value, this value will be used for calculating the outer frame. And so I can literally put whatever arbitrary value I want, and the stack will calculate it using that. So if I use just these two frames, I can arbitrarily change an arbitrary chunk of the cold stack. Of course, on return, if I just use these two frames, on return I will break the program, because imagine that I put something else here, even the thread initialization frame. Now, when I return back from the target function, I hit this, and then I don't return to the main module, which is my code. I will return to the base thread init tank, and we'll crash the program. So we need a way to also restore the stack after we did this. And so we use this, what we call the synchronization frame. We chose a job gadget. It's not required to have a job gadget. It's literally our choosing because it was convenient. Jump RBX is encoded in 2 bytes, so it's very convenient when you're trying to locate a gadget. But you can, whatever it is, if you want a push ret, if you want a jump, if you want a call, because RBX is completely under your control. So whatever you want to call, cop, job, ROP, you can use it. Now, these 3 are the technique. So with these 3, you can implement the technique. But because it's a bit too obvious what we're doing by using this job gadget here, we also decided to introduce a conceal frame just to conceal the fact that we are doing this. So the conceal frame is literally an aesthetic function, and you can use an arbitrary number of conceal frame either here and before the jump, before the desync gadget. This means that you can create this kind of frames in a variadic fashion. You can create whatever you like, practically, whatever combination you like. Of course, always remember that the stack size is limited, so you can overflow your stack after a while. So just think about that. Now, on return, what happens? The main module is completely hidden now. On return, I just hit the RSP X, which is a stack pivot. I go to the jump RBX. RBX will contain a function that I previously, of course, implemented, and it will just remove all these frames and restore the original return address here so that the execution doesn't crash. So literally, this is the technique. And in terms of how the cold stack look like, well, the cold stack is unwindable to the bottom because in RBP we placed a reference to base thread init tank. Very easy. So these are the 4 frames selected by the technique, and these are exactly what we want to check if we want to detect this technique in action. So how do we detect this? Can we detect this? Well, you can see, let's look at this again. So we have set thread stack guarantee, and then we have discard virtual memory, which is already kind of strange function. And then we have perf query instance. It doesn't make any sense. So logically, the frames are unwindable, of course, but the frames selected are not necessarily logically valid. So how can we use this information to hunt for this technique? Well, we can just look at the bytes, the instruction, prior the return address of a frame. So if you understand how the call stack is created, every time I do a call, I allocate a frame in the called function, in the callee. So what I expect when I look back is to find a call that justifies the creation of the next frame. Instead, I find this, which is nowhere near a call, and this is bad, right? So this is exactly how you hunt for this technique. What we would expect to find as the instruction before the return address of a frame is one of this. So we can call, we can perform a long call, a far call, a near call, or a call to a register, or a relative call, or a system call. But that's it. So if I take the return address and I subtract 7, 6, 5, or 3, 2, I expect one of these byte patterns. If there is not, if I find something that is not one of these byte patterns, there is something wrong. So we can develop an algorithm, a full algorithm this time. And I can go and check for, I'll just go through all the stack frames, and I will just check the previous call instruction. Now, if there is a non-resolvable frame, I detected the reflection. If there is a desync gadget at the return address, then it's Stack Moonwalking. If I don't find a call as the previous instruction, there is a call mismatch, and in case you can create something better, like in case you can create a pattern with a call and a jump, what happens? Well, I'll have to check the address that you called. Because if by mistake you manage to create a fully legitimate chain, I can still check the address that you're calling to ensure that that address is a pointer to the next function. And like this, we have discrete success, I would say, against this technique. So this is the technique in running. We have our stack, which is fully unwindable, but we can see that it detected already something, and it's observing some byte patterns that is not expected, and it can identify that something wrong is happening. Of course, there is something that we place directly in the POC, unless it's a JIT process. So there are some false positives. Now, there are not many, but there are some false positives. So if you look, for example, at this is WinDebug. But there are, like, if you debug the SIGWIN, not if you debug. If you inspect the SIGWIN DLL, if you inspect other kind of JIT processes or other processes, you will find that there are always anomalies. And we tested the Eclipse algorithm in a lot of circumstances in various Windows builds. And there is also, I mean, I would like you to focus on the false positive rate. It's not great, it's not massive, but there is still a chance for an attacker to just use, I mean, JIT processes have been historically abused because they contain RWX section by default. The CLR really does some crazy stuff in it, so it's really common to be abused, and this is another kind of proof that JIT processes are bad because they gave us another opportunity to blend in with the noise. Now, I don't know how I managed to be so fast today. So towards the future. So I want just to give you some additional research avenues. And before doing this, I will just give you the key takeaway of this presentation. And of course, the public POC is available here. You will find some update very soon because we need to upload the clips and other material. This POC, of course, as I said, is designed to obfuscate the stack at runtime. While you're obfuscating the stack while sleeping, I would recommend to use probably another kind of technique like stack cloning or stack hiding. Why? Because the more you are executing this, the more you are keeping the stack with the 4 malicious frame there, the more you give a chance to an hunter to actually go there and understand that something dodgy is going on. As I said, it is possible to use a lot of different techniques like jump, cop, and drop gadgets. You're not really forced to use the jump, the desynchronization technique as we actually implemented through the jump RBX. And it is possible to create arbitrary length chains, of course. And it is difficult, but not impossible, to create completely valid cold stack. So in Windows, there are certain patterns are difficult to find. You probably need to search all the System32 DLL list, but there are patterns that actually contain call and jump one after the other. Now, a closer inspection may leak that you're doing something dodgy, but they may be useful for evading automatic detection. There are some unanswered questions, of course, in this call. And for example, I didn't show you how you can implement this technique. I mean, this is cool as a POC, but can I implement it in my own implant? Or it is possible to integrate this POC with, for example, sleep encryption, which is another topic that is fancy and trending. But it's also very important to maintain stealth during sleep times. It is possible to bypass Eclipse. And what about Intel chat? Like, it's something like the technique is dead after Intel chat, or we can do something about it. So if you are interested in these topics, I don't know, how many of you are coming to NOET this year? 1, that's great. So we will talk, there is another part of this talk which is we will be held at NOET, and we will discuss more about the deeper implementation of this technique. We will present another technique which is designed to obfuscate forward, and it's a forward obfuscation of the cold stack. And then we will present another technique that is meant to go backward. So it's not full moon, but it comes close to that. I want to leave you with a sneak peek about how it's possible. I mean, a lot of people have said you can't implement gargoyle with Stack Moonwalking, because gargoyle is the problem of encrypting what you're executing. So you need to have an offload mechanism to decrypt after you come back from the sleep. So this is just a little video. So just a spoiler, and for sleeping beacon, it's a modified version that I modified to check the cold stack even in user requested wait state, because usually it doesn't do it. And so what you can see is that this is a PowerShell script just to automate. So we start an SSH, and we are doing vanilla process injection. So I'm injecting on the heap. So what you would expect is to find the stigma, malicious frame, right? It's clean. All the scans are clean. PSIV, Moneta, and for sleeping beacon are clean. But if you look at this, you will find the message box, the 4 frames selected by Saiyan Moonwalk, and the technique just went through. So it is possible to implement gargoyle even when you're spoofing the stack this way. It's just a bit creative, I would say. But that's it. And this is I mean, honestly, we're lucky because I will send you to lunch early. Seems like great outcome in the end. So thanks a lot. This was the talk.